Okay, here in lecture 12 I want to develop a general range equation. Actually, I prefer to solve the problems independently, but I'm just going to show this range equation formula. That way we can ask the question, what is the best angle, right, for our cannon to fire? So how do we proceed? Well, first thing we want to do is we're going to find, well, how long does it take for the cannonball to leave the cannon and then land on the ground in general? When last time we said, well, we need to know what the time is at the apex, right? So that is when v sub y is equal to 0, which is equal to v naught y minus g times t. So solving for this, we get that t is equal to v naught y over g. I think I made a mistake in the last cannon problem, and I should have doubled this time, because the time to hit the ground is actually twice this amount. So the delta t that we are interested in, right, which is how long it takes to go from here to here, this delta t is equal to 2 times v naught y over g. So it's twice this value here. I think I forgot to do the factor of 2. But what's the factor of 2 between friends? So I'm going to now use this value for the time in the displacement. But I'm going to call the displacement the range. So we'll call it r. And that's going to be equal to v naught x times the time. Well, I'm going to use for the time this delta t here. So this is equal to v naught x, 2 v naught x, v naught y, all over g. Well, v naught x and v naught y, you'll recall, right, are equal to the magnitude v times the cosine of theta, and v naught y is equal to the magnitude of v times the sine of theta. So I can substitute those values in here, and I get that this is equal to 2 times, we have a v squared over g, because we have 2 v's in here, and we have the sine of theta times the cosine of theta. And I think I alluded to this earlier, that we would use a trigonometric identity. And as it turns out, there is a trig identity that we can use that says that 2 times the sine of theta times the cosine of theta is equal to the sine of 2 theta. So you can look that up in any trigonometry book, but it's true. And so this ultimately says that the range is equal to v squared over g, where v is the magnitude, times the sine of 2 theta. So other than using a gun with a higher muzzle velocity or going to a planet with a smaller acceleration due to gravity, what can we do to increase the range of this? Well, when can we maximize the sine of 2 theta? Let's just think of it as the sine of alpha, where alpha is equal to 2 theta, so we don't have to keep saying 2 theta. So I'm going to rewrite this as alpha, and I'm going to note that alpha is equal to 2 theta. So when is the sine function maximized? Well, you remember that it had a minimum value of 0, that was at 0 degrees, and it had a maximum value of 1, which was at 90 degrees. So the answer is, when alpha is equal to 90 degrees, the sine of 90 degrees will be 1, and so this will be as big as it possibly can be. So if alpha is 90 degrees, that means that theta, which is 2 times theta is 90 degrees, this means that theta is equal to 45 degrees. And so the maximum range that you can get from a gun is at 45 degrees. So I'll write this as the 45 degree line. If I go higher, that's a terrible looking trajectory. If I go higher, the cannon will go higher in the air, but it will land shorter. If I go at a shallower angle, it will not go very high and it will not go very far. So the maximum angle that we can get is at 45 degrees. And that's neglecting air resistance. But we're not worried about that here. And so I think that's all I'm going to say about the 2D kinematics. There are plenty of problems to work on this, and some of these will be posted. I think that's all I'm going to talk about for 2D kinematics. The next thing we're going to cover is geometrical optics, because we haven't actually talked about any physics yet. I thought it would be nice to actually talk about some physics instead of just doing math. So that's what we'll be doing next time. Thank you.